In this video, I want to talk about how to graph exponential functions. And the easiest way to explain this is actually to work through an example. So I want to work through the example y equals 2 multiplied by 1/3 raised to the negative x plus 2 power minus 4. So we're going to graph this exponential function. First of all, we should say that the thing that really makes this an exponential function is this value right here, the 1/3 raised to the negative x plus 2 power, this part. And the reason is because that's a value here raised to an exponent, so this is an exponential function. The fact that this happens to be multiplied by a constant of 2, or that we're subtracting a constant of 4, doesn't really have an effect on the fact that the meat of this right here, is an exponential function. So for me, the way that I like to go about graphing an exponential function like this one is to follow a specific set of 4 steps. And I just like following this process because it's easy for me, I can remember it, and I find that it's a pretty quick way to get to the graph of this function. So what I like to do first is plug in the values x equals 100 and x equals negative 100. Now, why are we plugging in those random values? Well, the reason is because when we pick a very large value for x, the positive 100, or a very small value for x, the negative 100, a very negative value, we're trying to look at the end behavior of this function. In other words, we're saying, as we take x to be very, very large, what happens to this function? And as we take x to be very, very small, what happens to this function? What we're hoping to see is that the function will level out toward a horizontal asymptote, either on the positive side or on the negative side. So let's see what that looks like. If we plug in x equals positive 100 first, what we get is y equals 2 times 1/3 to the positive 100 here for x. We have this negative sign, so plugging in positive 100 actually gives us negative 100. Negative 100 plus 2 is a negative 98. So negative 98 minus 4. Now we bring in an exponent rule. So remember that when we have a negative exponent, in order to make that exponent positive, we have to move the whole term either from the numerator to the denominator, if it's in the numerator, or from the denominator to the numerator, if it was in the denominator. Here, this 1/3 to the negative 98 is in the numerator. So we need to move it to the denominator. So we say y equals 2 multiplied by, we put 1 in the numerator and put this entire 1/3 to the now positive 98, because we moved it from the numerator down to the denominator. So we flip the sign on the exponent and make it positive, and then we have minus 4. Now we need to focus on this 1/3 to the 98 power. Remember that when you have an exponent applied to a fraction, you can apply the exponent to the numerator and the denominator separately. So this is really like saying 1 to the 98 power divided by 3 to the 98 power. Well, 1 to the 98, doesn't matter what you raise 1 to, it's still going to be 1. So you're going to end up with 1 over 3 to the 98 power, and then minus 4. 3 to the 98 power just becomes a very, 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 very large number. So we could really think about this 3 to the 98 as infinity. This is going to become infinitely large. And here's where we start seeing what the value of y is going to end up as. So when this number gets very large, it goes toward infinity. When we take 1 divided by a very large number, the larger the number is, the closer 1 divided by that very large number gets to 0. You can see this for yourself if you take, for instance, 1 divided by 10, then 1 divided by 100, then 1 divided by 1,000, 1 divided by 10,000. The larger the value of the denominator gets, the closer you get to 0, which means that this 1 divided by infinity value, 1 divided by a very large number, is going to end up going to 0 essentially, or becoming a very, very, very small number. So what we have then is 1 up here in the numerator divided by a very small number. And again, 1 divided by a very small number will go toward positive infinity. This whole thing will become a very large number. So essentially we have 1 is equal to 2 multiplied by this whole fraction here will become an infinitely large value, or positive infinity. And so what we say then is when we have an infinitely large value here multiplied by 2, that's still an infinitely large value. Taking an infinitely large value and subtracting just 4 from it still gives us an infinitely large value. So we end up here with an infinitely large value for y. Contrast that with what happens when we take x equals negative 100. So for x equals negative 100, we'll go through the same set of steps, plugging in here negative 100 for x. Well, we'll get y is equal to 2 multiplied by 1/3. Negative 100, when we plug that in, we have a negative sign in front, so we'll get negative 100. Those negative signs will cancel, and we'll be left with positive 100. 100 plus 2 is 102, so we get 102 and then minus 4. Just like over here, when we apply an exponent to a fraction, we can apply it to the numerator and denominator separately. So we get y is equal to 2 multiplied by 1 to the 102 is still 1, and then 3 to the 102 is what we're left with in the denominator, and then we have our minus 4. And again here we start playing with our infinities. 3 to the 102 is going to be an infinitely large number, so this is going to look like infinity. 1 divided by an infinitely large number becomes an infinitely small number that eventually tends toward 0. This whole thing here, 1 over a huge number, gets very, very, very small, and so this entire term is going to go to 0, which means we're essentially going to be left with 2 times 0 minus 4, or 0 minus 4, or negative 4. So here's where we get to the second step of graphing exponential functions. We plugged in 100 and negative 100. When we do that, we're always going to get one value that tends toward positive infinity or negative infinity, and we're always going to get one value that is a real number. So here we have the infinite value, and here we have the real number, negative 4. The real number is going to represent the horizontal asymptote for the exponential function. So we'll go ahead and say here that this is going to be the horizontal asymptote. As x gets very large, the value of the function is going to tend toward positive infinity. And so we'll see what these two look like more in a second. But the next step, once we've done these two, is going to be to plug in just a couple points to the function y here that are easy to evaluate. I like to use -1, 0, and 1 for x because they're usually easy to plug into the function. So if we plug in -1, if we start with that, so for x is equal to -1, what do we get? If we plug in here -1, we have a -1. Those negative signs cancel. We're left with positive 1. 1 plus 2 is 3. So we're going to end up with y is equal to 2 times 1/3 to the 3 minus 4. 3 to the 3rd is 27, so we're going to end up with 1 over 27 here. When we multiply that by 2, we're going to get 2 over 27. So 2 over 27 minus 4, and that's approximately equal to about -3.93. We could come up with the fraction value, but this will make it easy to graph. For x equals 0, when we plug that in, we're going to get 0 here plus 2 is 2. So we'll get y is equal to 2 multiplied by 1/3 to the 2 minus 4. Well, 1/3 quantity squared is 1 over 9, multiplied by 2 is 2 over 9, so we get 2 over 9 minus 4, and that's about equal to -3.78. And then if we plug in x equals 1, our last value, we get y is equal to 2 multiplied by, we'll have here 1/3, and then positive 1 here, we have the negative sign, so that turns into a -1, plus 2 is a positive 1, so we get 1, and then minus 4. 1/3 to the 1 is still 1/3, multiplied by 2 gives us 2/3 minus 4, and the value we get is about -3.33. So if we want to graph this then, we have these 3 coordinate points. Let's go ahead and move this for a second. If we plot those 3 points on coordinate axes, we find that we get this. And let's remember here that when we said for x equals -100, y was -4, and for x equals +100, we got y equals infinity. these 3 points that we plotted here on the graph are the values for -1, 0, and +1. What we can see is that they form an exponential curve, and the curve is approaching this horizontal asymptote at -4. So if we go ahead and sketch in a horizontal asymptote here at y equals -4, then we can say that the graph of the exponential function, if we connect these points, might look something like this. So it's skimming along the horizontal asymptote, and it hits these 3 points here. And then as x gets large, the curve is going to tend up toward positive infinity, so it might look something like this. And we can see how this curve matches our function. We found these 3 coordinate points, and when we plotted those, we got these 3 points on our set of axes. We can draw in our horizontal asymptote that we found, y equals -4. We know that when x gets very large, as we get to the right-hand side of the graph here, that the curve tends up toward positive infinity, so it makes sense that it would curl up and to the right like we're seeing that it does. And so with all that information in mind, we simply just sketch out the curve by connecting the points. So when it comes to sketching exponential functions, we just saw how to sketch one from scratch. But keep in mind that you'll often have to deal with these kinds of functions as transformations. So for instance, you might be given the problem, sketch the graph of this exponential function here, given the graph of y equals 1/3 to the x. In other words, you have this exponential function y equals 1/3 raised to the x, and you've been given its graph. So the graph that we see here, this is the graph of 1/3 to the x. And you're supposed to use this graph to get to the graph of 2 times 1/3 to the -x plus 2 minus 4. So what you have to realize when you're asked to do a problem like that is that this is just a series of transformations. And I think the most helpful way to go about this is to list out those transformations one step at a time. So what you want to say is that equation number 1 is the original equation that they gave you. So that's going to be y equals 1/3 to the x. That's what we're starting with. That's what we have the graph of. Now, one step at a time, I want to get from this equation to the equation that I've been given. So in order to do that, I already have the 1/3. I have this raised to the x power. The first thing I would need to do is change the x to a -x. So I want to call equation number 2 whatever I get when I substitute -x for x. So 1/3 to the -x. My next step would be to add 2 to the exponent. In other words, y equals 1/3 to the -x plus 2. Then from there, I want to multiply that value by 2. Y equals 2 times 1/3 to the x plus 2. And then my last step that gets me to the original equation is to subtract 4 from that. So y equals 2 times 1/3 to the -x plus 2, and then minus 4. Now we want to walk through these transformations one at a time. So we already have the graph of this first one. What happens when we change x to -x to get to this second equation? Well, when you replace x with -x, what you're doing is you're flipping the graph over the y-axis. You're creating the mirror image of the graph over the y-axis. So what we want to see here is that we have this curve. It's intersecting the y-axis here at the point 0, 1. So we know that that's going to be on the graph of y equals 1/3 to the -x, because these two curves are going to be mirror images of each other over the y-axis. So if we go ahead and try to sketch that curve, it's going to look something like this. We're going to have the curve coming down and then coming closer, intersecting at 0, 1, and then sharply coming off here and going out toward infinity that way. So something like this. That's the horizontal asymptote. So that's the second curve. Then to go from this second equation to the third equation, when we add a plus 2 like this, it's going to shift the graph over 2 units to the right. So we need to look at this graph of the second equation we had and move all of the points on it 2 units to the right. So this point needs to come over to this spot right here. We know this point at 0, 1 needs to come to about right here. So then if we connect those, we're going to have a graph that looks something like this. And this is going to be the graph of our third equation. So that'll come along the x-axis like that. That's the graph of number 3. To get the graph of number 4, we simply have to multiply this by 2, which means that every y value gets multiplied by 2. So we can take each of these points, for example, this point here at 2, 1, and multiply the y value by 2. The y value is 1, so the y value will become 2. It'll move up here. This y value is 2. It'll get doubled and move up here and become 4. So when we then connect those points, we get something that looks like this and comes out along the x-axis. And then to get to the fifth equation, when we subtract 4 from this curve, it's just going to shift the curve down by 4 units, so we can take these points and move them all down 4 units. So 1, 2, 3, 4 to about here, and then 1, 2, 3, 4 to here. And then remember that all of these curves have a horizontal asymptote at y equals 0. So if we're shifting the curve down, that means we're going to have a horizontal asymptote at y equals -4. So we could go ahead and sketch that in. We know then that if we sketch the curve roughly through these points here, we're going to get something that looks like this coming down here, intersecting these points, and then comes hard to the left and skims across this horizontal asymptote that's at y equals -4. And so what we said then was that we started with this initial curve, this number 1 curve here, of y equals 1/3 to the x. We knew that this curve was the mirror image of that over the y-axis, that this curve was shifted to the right by 2 units, and that this curve got stretched by a factor of 2 vertically. And then finally, we were able to take that curve and shift it down vertically 4 units to get to this last curve here that we sketched, and that is the curve that represents 2 times 1/3 to the -x plus 2 minus 4, which we were able to get to through a series of transformations, starting with the graph of 1/3 to the x.